Hi everybody, Physics Ninja. Today we're going to look at calculating the magnetic field due to a current loop, a square current loop, and we're going to evaluate that magnetic field at a point that is above the square loop and it's a certain distance height above the plane. Okay, I previously did the problem where I calculated the field right at the center of the loop, right here. And I had a request from a student for help on setting up the problem. What if I want to move that point a little bit above the loop? Okay, how would it change the approach? Anything similar? So anyway, we're going to go through all the steps. This is a little bit more mathematically challenging than the first case. At the end, our result, if I take the limit where h is 0, I better go back to the previous video and get the same result. So that'll be kind of a check we can do to make sure that the math works out. All right, remember, subscribe to the channel, like the video if you like it. Ask any questions. I'll try to get back to you as quickly as possible. All right, let's get started. All right, so let's first start with just some basic definitions here. So here's our Biot-Savart that we're going to evaluate. And this is for a general, any element of current dl, right? It has a little length dl, so I can consider this little element dl. First thing we have to define is all of the vectors here. So we have a vector r and a vector r prime. So let's start with just some basic definitions. So the vector r is a vector that goes from, let me just write it down over here. So r is the point of observation, right? Where do we want to evaluate this magnetic field? In this case, I'm going to take everything with respect to the origin here. So that vector r goes over here. That's the vector r. So in this case, it's pretty straightforward. It has 0x, 0y, and it only has a z component, right? So the vector r, I should be able to write just as 0, 0, and some height z. In this case, the height z is going to be equal to h. Okay, but for now, let's just keep it as z, and I can place it anywhere I want. What else? We have a vector r prime. Okay, so r prime goes from the origin to the source, right? Okay, and the source is going to be any little current element along this loop. So if I take this particular one here that's in purple, the vector r prime should look something like this. Well, it has a y value and it has an x value, right? The x value is, its center here is at some value x. So I'm going to write that as x. We're just going to use prime notation for everything. So this here is the x component of that vector. What else? It has a y component. And look at the y value for everything here, for this little element here, is going to be negative and L over 2. Okay, remember the loop that I'm considering here is a square and the length of each segment is L. So if I take with respect to the origin here, this distance here would be L over 2. And I put the negative sign because, at least for this purple one here, it's on this side. And what else? It has no z component because I'm going to take this loop to lie in the xy plane. So it's 0. Okay, so that's pretty straightforward. The other thing we want to do here is we want to use symmetry as much as possible because symmetry allows us to really simplify our problem. Okay, and by symmetry, this is what I am going to consider. Let's imagine here I have another little element of length dl with a current I flowing through it in this direction. You should be able to remember, every current produces a field that produces a circle around that wire, right? So if I consider this little element of current, over at point P, it should look like a field that looks like this. This is the field produced by this little bit of current over here. Notice it has an x component, and it also has a z component, okay? Now how about if I chose a little segment on the other side? Okay. In this case here, I would find a magnetic field that would be like this. Okay. It also will have an x component and a y component. At the end of the day, I want you to notice that the total field produced by both of those segments is only going to result in a field in the z direction. Okay. The x components here are going to cancel out. So from symmetry, and you can do that with any actual segment over here. Okay, so from symmetry, B, although it's a vector, it should really only have a z component. So this is really all we're going to try to calculate. The other thing we're going to use from symmetry is that, imagine I label all of these segments, right? My Biot-Savart says I have to integrate the current over the entire loop. Well, imagine this here is the segment 1. It goes from here to here. Segment 2 is the next one. It goes from this corner all the way to this corner. Segment 3 is in the back, and segment 4 is this one. Well, I'd be able to write that the total magnetic field has to be the field due to segment 1 plus the field due to segment 2 plus the field due to 3 plus the field due to 4. All right, now you have to be able to convince yourself that at the end it doesn't really matter which segment I am considering. At the end, the only thing I'm really going to be interested in is going to be the magnetic field produced by one of these segments, and I'm really only interested in the Z component. Okay, so at the end, I really only have to calculate the field due to segment 1, and I'm really only interested in the Z component of that field. Okay, and I'm going to multiply by 4 because I have 4 different segments. Okay, so this is really the key to this problem here, just to make it much, much simpler. Otherwise, you're going to be doing this for about a week and a half. So we really just want to find the Z component of one of the segments, and I'm going to consider this segment only. Okay, I'm going to multiply by 4, and at the end, I really only need the Z component of that field, okay, because anything else that's in the X or the Y direction will cancel out by symmetry. All right, now let's go on the other page and set up the equations. All right, so let me go ahead and just write this out a little bit differently. So instead of writing my vectors kind of with this kind of form, I'm just going to write it as this is going to be Z multiplied by a unit vector Z hat. And the vector R prime then would be X prime. It has an X component. This is the Y component. And that's it. It has no Z component. All right, I'm really interested also in this term in the bracket. So that means that R minus R prime. Okay, just take the difference between both of those, and I'm doing R first. R minus R prime gives me Z. Z hat, and then I have to switch the sign over here. So I get minus X prime, X hat, and then plus L over 2 Y hat. All right, let's substitute everything in the Biot-Savart. And again, now I'm not going to integrate over the entire loop because I'm only interested in segment 1. Okay, so I'm going to write that as B. This is only for segment 1, but it's the total field right now. At the end, we're only going to take the Z component, but for now, we have mu 0 over 4 pi. It's pretty straightforward. And now, well, let's not really worry too much about this. I'm going to take out the current I. The current I is a constant. Take that out. All right, now what is DL for segment 1? Well, segment 1 is right here, the one I've highlighted in blue. All right, so how do we write DL over here? So I would write DL. It really only has a X component over here, right? The X-axis is over here, so I would simply write this as X, dx prime, and then it's really only an X component, right? That's the magnitude of it, of a little element, and this is the direction. Okay, so let me put that into my equation for Biot-Savart. So this is what it looks like. So we have dx prime multiplied by x hat. All right, all of this now is I'll change the color just to make sure we understand. This is a cross product here, and a cross product with the vector r minus r prime, which we evaluated right here. So this is z hat minus x prime, x hat, plus L over 2 y hat. So far, so good. And at the end here, what we need here is, this is the magnitude of that vector, and you have to cube it. Okay, so for now, I'll just keep this magnitude bracket like this, and I'm just going to substitute r minus r prime. All right, so we're basically just substituting the same thing, but keep in mind, at the end, we really need the magnitude of that term. So we'll do that on the next page. For now, let's just write it like this. X prime, x hat, and plus L over 2 y hat. All right, hopefully you can follow me, and this is over 3. All right, the next thing I want to do now is work on this cross product here. Okay, so let's go on the next page and do that. We have our expression for the total field produced by this little element over here. And again, the total field that I'm really interested in at the end, right, B that I really want, it really only has a Z component, okay? So how do I go ahead and I take a Z component? Remember, it's going to be 4 times the field due to segment 1, but only the Z component. So how do I do that? Well, I imagine I have a unit vector here, And if I take the scalar product with the field B1, right, it would look something like this. This would be 4 times z hat and dot, and this here might have a x component. This is B1 in the x component, B1 in the y component, and B1 in the z component, right? If I take the scalar product here, forget about these two components. The only thing I'm really interested in the end is to get the total field that's going to be 4 times the field due to the segment 1 in the z direction only, okay? And this is the total, okay? So this is the total field. All right, so the reason I want to say this is if you look back at this cross product now, well, so we have to be careful when we evaluate this. We have a x hat direction and with this, okay, with a z hat. If I do a cross product of x with a z, this here is going to give me a y hat component. Okay, this one here I'm really not interested in because I really only want the z component of the field. So let's go to the next one. X hat with this x hat. Oh no, that gives me 0. I don't have to worry about that. All right, so the only thing that you have to worry about for this cross product is really only the last term. Okay, and the last term is going to be this one. X hat with the y hat direction. If you remember from algebra, x cross y actually gives me z hat. Okay, so this is really the only thing I'm interested in. So let's go ahead now and write down our integral, but again, we're going to write down the total field. Again, it only has a z component. Well, maybe I don't really need this over here. All right, apologize for that. All right, so we have 4 times. And now this is the integral I want, except I only want the z component. So let's write down all the constants. So we have mu 0. We have our current I. We have 4 pi. All right, what else? We're going to integrate. And we're integrating dx. So this is going to go from minus L over 2 all the way to L over 2. Right? Because it goes all the way from here, minus L over 2, all the way to L over 2. All right, what else? This here is going to be dx prime. Now, when I take the product between this and that term, I still have this L over 2 term, so you can't forget that, and that's simply a constant. So I'm going to go ahead and put that to the front, L over 2. All right, and now I simply have this denominator, which I haven't touched, right? So this here, I simply have the exact same term. So it's z hat minus x prime x hat and plus L over 2 y hat. And it's the magnitude of that whole term, that whole vector, and I have to cube that value. All right, so we can simplify some of these terms in the front over here. This 4 can cancel out with this one, and that's pretty much it. Okay, you can basically rewrite this. All right, so now all we have to do is evaluate this integral, and that's it. That's our final result. Okay, so let's go work on this term over here. All right, so let's take our term and let's just rewrite it here. So we have a mu 0. We have the current I, the length of the square, and 2 pi. Just switch the order over here. And now I want to get rid of these absolute values over there. Let's actually write down the magnitude of that vector down there. Okay. Magnitude of a vector, again, I have to simply square each term and then take the square root. So that's why it's going to be 3 over 2 over here. And I'll switch the order so we have a x prime squared. The y component, I need to square that. That's L over 2. Got to square the whole thing. And then plus z squared. All right, what I would suggest now here is, so there's a couple ways to do this. All right, you can either look this up in an integral table. And in order to do that, what you have to do is you call everything in this bracket here, you call that some variable a squared, okay? Because it's a constant term here for this integral. It doesn't change. So really the integral that we're trying to solve is this one, right? Minus L over 2 to L over 2 dx prime, and it's really x prime squared plus a squared, all this to the 3 halves. All right, if you can't find this in an integral table, what I would suggest is just doing some trigonometric substitution. Okay.
So what this looks like, if I kind of redraw this kind of a little bit simpler,
if I'm at here at some point P, which is a certain distance away from the variable that I'm trying to integrate, okay, this would be A, and imagine I have a little bit of length here, dx, and I have a distance, this vector over here, which is going to be, again, this guy here is x prime. Sorry, it's dx prime. X prime goes from here to here. That means that this guy over here has a length x prime plus a prime, and take the square root of that to the 1/2. Okay. The easiest way to kind of solve an integral like this is to do trig substitution. So if you call this theta, automatically you could see that you can write tangent of theta. Okay. Tangent of theta would be x prime over a. So that means that x prime is a tangent of theta. Okay. If you want to do the substitution, you need a little element dx. So you can take the differential over here. A is a constant. If you take the derivative of tangent of theta relative to theta, it's secant squared of theta d theta. Okay, so I can then substitute that in over here. What else? What's this term over here? Well, x squared, I could substitute it in over here. So let me go ahead and kind of just walk you through this a little bit. We're not going to be integrating from L over 2 all the way to minus L over 2 because we're integrating over theta now. So we're integrating over some angle down here, theta min, all the way to some maximum angle like this. Okay. So we're integrating over angles. dx now is this guy, a secant squared theta d theta. And what else? Down here at the bottom, my x prime squared, or x prime is right here. Okay, that's a tangent of theta. So you have a squared tangent squared of theta plus a squared. Oh boy, you got to do about a week's worth of algebra, but this is what it ends up being. The nice thing about it here is you could take out a from this bracket. It becomes a cubed. So at the end, you're going to have you have a at the top and you have a cubed at the bottom. So it becomes 1 over a squared. And this integral over here, theta min, all the way to theta max. What else? We have secant squared theta d theta. And what about the bottom? The bottom here you have tangent squared theta plus 1. Oh boy, that looks really, really complicated. However, this here, the definition of this is secant squared of theta. So that really, really simplifies everything. So at the end, oh boy, we're going to have to go to the next page. Let's go to the next page and continue this party. Here's the integral here. Let's kind of simplify this a little bit. I'm going to go through this a little bit quickly here. This term was secant squared, but it's raised to the 3/2. So at the end, you end up getting theta min all the way to theta max. This term here ends up being 1 over secant of theta. And make sure you kind of work through that for yourself. At the end, 1 over secant is just cosine, right? So we have a squared. I'll just skip writing the limits for now, but we're just basically going cosine theta d theta. And that result is really straightforward. Okay? It's just sine of theta, right? And evaluated between both of those limits. Actually, you can see from symmetry that the angles are the same. They're just one of them is negative. So actually what you can do is just, this is really like negative theta max all the way to theta max, right? The angles are actually the same. And using some of the properties of the sine function, you can see right away you're simply going to get 2 times over a squared sine of theta max. Okay, so this was only this integral. Actually, if I wanted to know really what the field was, the field, if you go back previously, the total field, I had a constant in the front. Okay, the constant in the front was mu 0, the current, the length divided by 2 pi. And then I had the entire result for this integral. All right, so now we got to go back and substitute, get rid of a, and also get rid of this sine of theta max using our little triangles over here. All right, so we're just about done the problem. Bear with me. I know it's kind of mathematically tedious, but let's go ahead and write this. L over 2 pi. No, there's another 2 right here. For now, I'll just keep it like this. At the end, we'll simplify it. All right, so let's get rid of a squared. Well, a squared I had defined as this term, right? I had grouped 2 constants together. So here I had z squared plus L over 2, and that whole term squared. Let me just make sure I write this as a nice clear 2 so we don't make any mistakes. Okay, and now we have sine of theta max. So sine of theta max would simply be, let's do this nice big square bracket. It would be this distance right here and divided by this distance. So that would be L over 2 and divided by the entire distance here going from this point all the way to the edge. Square root. Again, now instead of writing a squared, I'm going to substitute everything over here. So this whole term here becomes z squared plus L over 2 squared. And then I have another L over 2 squared. All right, I have the same term here. One of them comes from the a, and the other comes from just doing the integral over here. All right, so the last final step, I promise you now, is just simplifying all of these things and then taking the limit. So let's go do that. Last page. Our last step now is just to simplify this expression. We have a 2 here. I'm going to simplify it with this one. We have L and L. That could be an L squared. Okay, so we're going to write our final expression now, BZ equals mu 0 I L squared divided by 2 pi. Now there's 2 terms over here. There's the first bracket, which is just 1 over z squared plus L squared over 4. Okay. And now there's a term here under the square root. This one you can simplify a little bit because you have L over 4 and L over 4. So when you combine both of those terms, you should get L squared over 2. Okay, so I've eliminated that a little bit. All right, and that's it. This is really the final expression. Now it looks kind of messy, but hey, that's physics for you. Now one thing we can do is what happens now if h or z, in this case the way I have it, is z equals to 0. Let's do that limit. In the limit that z equals to 0, so this term leaves, this other term leaves, and so what are we going to be left with? Let's have a look at it. So bz in that limit over here. All right, so what would simplify? So I'd still have the mu 0, I'd still have the I and the 2 pi. All right, careful. This whole term is not going to be there, right? The z is going to be equal to 0. So this L squared will cancel with that one. But there's still a 4 over here, so I have to bring that 4 all the way to the top. Okay, so that's this term. What else? Now I still have this term here under the square root. So let's work on this one. So this is simply going to be square root of L squared over 2. So it's going to be L over the square root of 2. All right, this can be simplified a little bit. That 4 and the 2 can cancel out. And at the end, the final expression that you get is 2. I'll bring the root 2 all the way to the top. And mu 0 I divided by pi times L. All right, if you go have a look at kind of the previous result that we had, this is exactly the same result that I presented before. Okay, so that's good. That's a good check. And the general result for any point that's a height h above, again, all you could do here is just substitute z for h, and you're going to get the field over here at point h. But that's it, folks. All right, hopefully that made sense to you. Hopefully the steps make sense. Again, it's a little bit longer if you do the trig substitution. If your professor allows you to just look up an integral table, you might be able to find that one in a good integral table. All right, thanks for watching.